In this video, we will continue our midterm 2 review by looking at some more parameterization examples. So in these midterm review videos, there's no way that I can cover every single type of example that we've seen over the course of the last few weeks. So it's important to keep in mind that the questions that I choose to do during these review videos are problems that I feel like would be good practice questions that involve concepts that we've covered in the last few weeks that are very important. But it does not mean that these are exactly what the test questions are going to be like. It also doesn't mean that any type of problem that I don't do during these review days won't show up on the midterm. It definitely could. I can't cover everything in one day. All right, so here's the next example. Let's find a parameterization for x squared plus y squared equals 16 that is at 0, negative 4 when t equals 0, and it goes clockwise. All right, pause this video for 2 to 3 minutes to try this question. 4, 3, 2, 1, pause the video. Pause it for about just 2 to 3 minutes this time to try this question. All right, so hopefully you've done that. Hopefully you've paused it for about 2 to 3 minutes to try this. So let's begin to talk about it together. So x squared plus y squared equals 16, if we draw a sketch of that. So that's a circle, and the radius of the circle. So let's sketch in our circle. And the radius is 4. So it goes out to the point 4, 0 here. And then the other side, it goes to negative 4, 0. At the top, it's 0, 4, and at the bottom, it's 0, negative 4. So we need to be starting at 0, negative 4 at t equals 0. That's what this question says. Okay, so this is going to be a non-standard parameterization, because the one that we're most used to that involves like just cosine and a sine starts at the rightmost point of the circle. It starts at 4, 0. But let's use that as our starting point to talk about this. So I'm going to organize my work and probably end up doing a few iterations before I get to the right one. So I'm going to sort of keep track of which parameterization I'm trying, and then where we are at t equals 0, just as a starting point, and then I may add more to this as we go. So in the very first parameterization that I'm going to try, let's try x equals 4 cosine t and y equals 4 sine t. That's sort of the typical one that we'd see for something like x squared plus y squared equals 16. And I need a parameter interval, so to go all the way around, let's say t goes from 0 to 2 pi. All right, so if we do this, if we choose this parameterization, if we plug 0 in for t, we get that we're at the point where x is 4 and y is 0. Okay, so that's already not where I want to be. I don't want to start here. Okay, so I'm going to put a sad face. This did not work out. Okay, I'm not at the right starting point. Okay, so let's choose a different parameterization. Okay, so I'm just going to make another row into this table. So that time I started at 4, 0. So I sort of need to switch the roles of the x and the y. I'd like to have the 0 first and the 4 second. So maybe let's switch the x and the y equations. And let's do x equals 4 sine t and y equals 4 cosine t. But I know that's not going to be quite right, because that'll just give me 0, 4. I need 0, negative 4. So let's put a negative sign in front of what y is. I'm going to make it negative 4 cosine t. And my parameter interval will be 0 to 2 pi again. So if we do this, if I plug 0 into this now, x is going to be 0, and y is going to be negative 4, because that's how I sort of built it. Okay, so it's got the correct starting point, but now is it going in the correct direction? So the way we can check is by plugging in another t value. If I plug in something like pi over 2, so this should be a quarter of the way around the circle. If I plug pi over 2 in, my x coordinate is going to be 4, and the y coordinate is going to be 0. So that's 4, 0, which means we are sort of trending this way, which is counterclockwise. Okay, so we don't want that either, because this one's going counter. The abbreviation for counterclockwise is CCW. That means counterclockwise, but we want to be just going clockwise. Okay, so far our first two tries haven't worked. Let's see if we can iterate and just, continue to get closer to what we want. So what needs to change is, after we begin at 0, -4, instead of going in the positive x direction, as this path did, we need to go in the negative x direction. So we need to go this way. We need to go this way. So let's change the sign of x. Let's make x -4 sine t, but let's keep y the same. -4 cosine t, because y was changing in the way that we needed it to. Y was getting bigger. Okay, in my interval, I'll go from 0 to 2 pi again. And if we plug 0 in for the t, we end up getting 0, -4. If we plug pi over 2 in, this time we will get -4, 0, and that is going this way, like we need it to. So this is going clockwise. Clockwise. CW means clockwise. Okay, so I'll put a happy face. We are excited about this. So this parameterization was the one that works. So one of the things that this example hopefully demonstrates is when we're doing a parameterization question that's very specific about properties that the parameterization should have, like the starting point or the direction, we may have to iterate, which means, try something, realize what about it is not right, try to fix those things, and get closer and closer to a correct answer. So it took us 3 tries to get there, but we got there. All right, so let's do another example. For this problem, let's find the intersection point of the lines. So the first line is described by these 3 equations for x, y, and z. And the second line is described by these 3 equations for this x, this y, this z. All right, so pause the video for about 3 minutes to try this question. It's likely not going to be enough time to finish the problem, but I mostly want you to think about how you'd begin. 4, 3, 2, 1, pause the video. Pause the video for about 3 minutes to try this question. And again, don't worry about trying to finish in this amount of time. I want you to be thinking about what the key steps would be, especially the key steps for beginning. Okay, so let's talk about this together now. So I'm going to call this first line, line 1, and the second line I'll call line 2. So there is an important hypothetical that I want to consider here. Because if the way you thought about this was, oh, I want to find an intersection point, so I set some x's equal, I set some y's equal, I set some z's equal, and then try to solve those, it turns out it doesn't work. And maybe while you were pausing the video, you realized that there was an issue with that because you ran into a problem when you try to solve. So I want to try to illustrate why with a picture. So we have some line. I'm going to call this one line 1. And we have this other line, line 2. And there's some intersection point. So this question says that there's some intersection point, and we want to find that intersection point. So with these parametric equation problems, they sort of represent a particle or some object moving along the curve over time. So hypothetically, let's just say that with line 1, at t equals 0, we're at a point like this. And then at t equals 1, we are a little bit further. So let's say this is where we are at t equals 1, and we're traveling this way. And by t equals 2, we reach that intersection point. And then, we'd keep going, Eventually, we're maybe here at t equals 5 or something. Okay, so the particle that's moving along line 1 reaches that intersection point at some time. So the particle that's on line 2, maybe it's over here when t equals 0. But the particle at line 2 doesn't necessarily travel at the same speed as the one along line 1. So maybe To get to this point, it takes 5 seconds or 5 units of time. And it's here by t equals 10. And it's here by t equals 15. And maybe it's only here at the intersection point by t equals 20. And then so on and so on. So this particle is moving this way. So the issue that might show up is, even though both of these particles arrive at this same point, they might not get there at the same time. Okay, so I want to write this as a takeaway, because this is an important key idea. So the particles might reach the intersection point at different times. And that's a problem. That's a problem that we're going to have to work around. Okay, so because they might arrive at that intersection point at different times, what we can do is we can assign different variables for t in their equations. Okay, so what I'm going to do is I'm going to let t1 be the variable in line 1, and I'll let t2 be the variable in line 2. And that's really important to do. If I don't do that, if I don't pick different variables in these two equations, I'm assuming that both of the particles get to that intersection point at the same time. But the problem doesn't specify that they have to get there at the same time. Even if they get there at different times, that doesn't change the fact that the lines would intersect. Okay, so let's do this. So let's assign different variables for the first, for time in line 1 and time in line 2, and solve. All right, so the first equation becomes x equals -1 plus 2t1, y equals 5 minus 4t1, and z equals 8 plus t1. The second line is x equals -2, should be a -2, -2 plus 3t2, y equals 7 minus 6t2, and z equals 4t2. All right, so we have our two lines. This one's line 1, this one's line 2. Okay, so now because we do have the different time variables for these, now we can actually set their coordinates equal. So for example, I actually think the z coordinate equations look the simplest, because in line 2, it's just 4t2 on the right, and that looks really simple. Let's set those equal. So I'll set 8 plus t1 equal to 4t2. So I have one equation now, two variables. Well, that's not going to be enough to solve. Let's also get another equation. So if I set their y coordinates equal, we get 5 minus 4t1 equals 7 minus 6t2. So now we just have a system of equations. But we know how to handle these from algebra. So in this first equation, I could isolate for t1, and I get t1 equals 4t2 minus 8. And we could substitute that into the next equation now. So if we do, we get 5 minus 4 times t1, which is 4t2 minus 8. And then this equals 7 minus 6t2 on the other side. So now from here, it's just some algebra. So we get 5 minus 16t2 plus 32 equals 7 minus 6t2. Okay, so on the left hand, so let's move all the numbers to the left and all the variables to the right. So if I add 16t2 to the right, we get 10t2. And if I move all the numbers to the left, we get 30. And dividing, we get 3 equals t2. All right, so we know what t2 is. That's the time that the second particle, the particle in the second line, should reach that intersection point. Okay, so at this point, I could take that time, plug it into the second line equation, and get the intersection point. But let's just be really, really thorough. Let's just make sure that the first particle on line 1 is also going to reach there at the same time. sorry, not at the same time, but what I mean to say is at whatever time, let's figure out the time that the first particle reaches that intersection point as well. Okay, so if 3 equals t2, I can plug that into this equation here to figure out t1. t1 equals 4 times t2, which is 3, minus 8. And that's going to be 4. Okay, so that's interesting. t2 is 3, t1 is 4. So that matches up with sort of what we were seeing in the picture in terms of just the times that the particles reach the intersection might be different. All right, so now let's just do a check. Let's just do a check where each line is at that time. Okay, so at t1 is equal to 4 on line 1, we reach, so let me zoom out a little bit to the top so I can see the equations for x, y, and z. So if you plug 4 into this, the x coordinate is 7, y is negative 11, and z is 8 plus 4, which is 12. Similarly, at t equals 3 on line 2, we reach, it turns out the exact same point. So if you plug 3 into negative 2 plus 3 times 3, you get 7. And in the other equations, you'll also get negative 11 and 12. So that's good. So that's making sense. So we have our intersection point. Our intersection point is 7, negative 11, 12. And that is our answer.